Welcome back to Machinery and Technology. Today, we're diving deep into the fascinating world of railway construction technology. Often associated solely with industrial transportation, railways play a much broader role. Military vehicles, for instance, can be swiftly moved by rail, ensuring rapid deployment. Moreover, railways demonstrate remarkable resilience in the face of natural disasters. Damaged tracks can often be repaired and reactivated quickly, providing vital transportation infrastructure in times of crisis. As we can see, railways are indispensable to the development and security of nations worldwide. To build a railway, the journey begins with raw steel. This material is transformed through a series of intricate processes into the familiar grooved rails that guide trains. Molten steel is poured into molds, creating large blocks known as blooms. These blooms are reheated and then passed through a rolling mill, where they are squeezed and shaped into the iconic I-beam profile. This profile consists of a head, web, and base, providing the necessary strength and stability for railway tracks. After shaping, the rails are carefully cooled to prevent warping and are then subjected to rigorous inspections to ensure they meet the highest quality standards. Finally, the rails are cut to precise lengths, drilled, and secured to the supporting sleepers. Modern railway track production is highly automated, incorporating advanced technologies to guarantee consistent quality, durability, and precision, ultimately laying the foundation for safe and efficient train travel. Traditionally, railway tracks have been constructed using flat-bottomed steel rails laid on and secured to timber or concrete sleepers, known as ties in North America, with crushed stone ballast placed beneath and around them. While this basic design has remained largely unchanged, modern railways have introduced several advancements. Continuously welded rails, attached to sleepers with base plates and resilient fastenings, have become the norm for high-traffic lines, reducing the need for joint maintenance. The use of pre-stressed concrete sleepers has increased in regions where timber is scarce or unsuitable, offering greater durability and load-bearing capacity. To enhance track stability and drainage, crushed stone ballast remains a common choice. However, advancements in ballast management, including the use of geotextiles and specialized drainage systems, have improved track performance and reduced maintenance costs. Additionally, the development of composite sleepers and alternative rail materials has expanded the range of options available for track construction, tailoring designs to specific environmental and operational requirements. Modern railway tracks typically employ hot-rolled steel rails with an asymmetrical rounded I-beam profile. This configuration provides optimal strength and stability under the immense loads and stresses imposed by high-speed trains. Unlike other applications of iron and steel, railway rails require exceptionally high-quality steel alloys to withstand the rigorous demands of heavy-duty rail traffic. Over decades, significant advancements in materials science led to the transition from iron to steel, resulting in substantially stronger and more durable rails. The capacity of a railway track to support heavier and faster trains is directly correlated to the strength and quality of its rails and associated track components. Historically, North American railroads employed rails 39 feet in length, a standard dimension that facilitated transportation in gondola cars. As gondola cars grew larger, rail lengths were correspondingly increased. Today, rail lengths vary widely, ranging from 12.5 meters to 100 meters or more. Regardless of their length, rails must be joined together to create continuous tracks. This is typically achieved through the use of rail joints, joint bars, or welding techniques. Railroad thermite welding is a technique that leverages the intense heat generated by a highly exothermic chemical reaction to join two rails together. In this process, the ends of the rails are securely positioned within a specialized mold. A mixture of aluminum powder and iron oxide powder, known as thermite, is ignited in a crucible. This reaction produces molten iron and slag, which are channeled into the mold. The molten iron fills the gaps between the rails, creating a strong weld. To fine-tune the weld's temperature and composition, various additives and alloys can be incorporated into the thermite mixture. This precise control ensures that the welded joint meets the stringent requirements for railroad tracks, ensuring their safety and durability. Thermite welding of railroad tracks. Thermite welding is a process used to join railroad tracks together by generating intense heat through a chemical reaction. The process involves several key steps. Preparation. The initial phase entails gathering necessary materials and equipment. Consumable materials include thermite, a mixture of aluminum powder and iron oxide, sand mold, crucible, sealing mud, high-temperature matches, grinding wheel, propane, oxygen, and hoses. Auxiliary equipment such as molds, slag trays, crucible forks, sand mold fixtures, and covers, along with tools like rulers, thermometers, clamps, crowbars, preheat frames, and steel wedges, are also required. Additionally, machinery like rail saws, polishers, and portable grinders are utilized. Railroad track preparation. Before welding, the track section is prepared by removing rail fasteners from both sides of the welding end. The rail ends are then thoroughly cleaned and dried to ensure a clean surface for welding. Precise alignment of the rail ends is crucial, with a specific gap maintained between them. A fixture is installed upwind to prevent wind from affecting the welding process. Sand mold and sealing. A sand mold is carefully placed around the rail ends, with a pouring hole slightly trimmed to prevent sand particles from falling into the molten metal. The mold is secured using clamps, and sealing mud is applied to prevent leaks. Preheating and crucible preparation. The rail ends are preheated using propane and oxygen to prepare them for the welding process. While preheating, the thermite mixture is prepared and poured into a crucible, with a high-temperature match inserted. Ignition and thermite reaction. Once preheating is complete, the crucible containing the thermite is placed on the sand mold and the match is ignited. The thermite mixture undergoes a vigorous exothermic reaction, producing intense heat that melts the rail ends and creates a strong bond between them.
Primer again. Primer number 2. Here you go, that one. What are the chemicals in that we're breathing in?
Cooling and finishing. After the reaction, the sand mold and slag tray are removed, and excess thermite is cut away. The welded area is then ground to ensure a smooth and even surface. Finally, the track is inspected to verify the quality of the weld, and any necessary cleanup is performed.
We like to check what it's like before we break it off. We're going to go a little bit early because that way we can see if it's liquid or not. So if it's too early, it'll be liquid. And it's not. It's just a little bit liquid, look, just a few little.
The traditional method of welding rails, aluminothermic welding, involves the use of a filler material, leading to weaker welds and extended cooling times. In contrast, flash butt welding is a solid phase process that directly joins rails without any additional material. This method produces superior welds with enhanced strength, fatigue resistance, and material flexibility. By eliminating the need for collars and ensuring material consistency, flash butt welding offers significant advantages. The process utilizes basic electrical principles, creating heat through short-circuiting and then forging the metal together. With a maximum amperage of approximately 1000 amps, the machine typically operates at 600 to 700 amps during the welding cycle, reaching temperatures of 800 to 900 degrees Celsius. Its versatility allows for placement on the track, adjacent tracks, line side, or even in factories. A major breakthrough in this technology is the ability to simultaneously weld and stress rails, significantly reducing production time. This capability enables completion of both processes within a single shift. Moreover, the machine's computer system provides real-time information during the weld and collects extensive data for subsequent analysis, particularly when troubleshooting production issues. The evolution of railroad maintenance has been marked by significant technological advancements. In the early days, manual labor, often performed by Gandhi dancers with shovels and beaters, was the primary means of maintaining track ballast. Rails were manually jacked up to allow crews to access and compact the ballast beneath. This laborious and time-consuming process was prone to human error. Modern railroad maintenance relies heavily on specialized machinery. Tamping machines, in particular, have revolutionized track upkeep. These machines not only compact ballast but also perform additional functions such as lining and lifting rails. Known as production tampers in North America, these machines have greatly increased efficiency and accuracy. Tamping machines are designed to ensure the integrity and safety of railway tracks. By packing ballast beneath the sleepers, these machines help to prevent track sag and maintain proper rail alignment. This is crucial for providing a comfortable and safe ride for passengers and freight. Additionally, by combining tamping and lining functions into a single machine, railway operators can save time and reduce costs associated with track maintenance. Here's a revised paragraph with more depth and clarity. Ballast, over time, undergoes a process of degradation. Its sharp, angular edges become rounded due to abrasion, reducing its ability to interlock with neighboring pieces. This decreased interlocking compromises the ballast's structural integrity and its effectiveness in constraining the track. Additionally, the attrition process creates fine particles, akin to sand, which can mix with water to form a sticky, concrete-like substance. This mixture hinders both track drainage and the ballast's flexibility to accommodate track movement under traffic. Ballast cleaning addresses these issues by removing worn and contaminated ballast, screening it to separate out undesirable particles, and replacing it with fresh, high-quality material. This process, which can be performed by specialized on-track machines without disrupting rail operations, offers a cost-effective solution for extending track life and maintaining its structural integrity.